Hello, Stat 200, and welcome to Lesson 9. This week, you're going to learn about chi-square tests. These tests can be used when we're examining the counts from one or more categorical variables. Chi-square is a common distribution. It's similar to the t-distribution in that it varies depending on degrees of freedom, but it's different in that it is skewed to the right. This is covered in Chapter 7 of the Lock 5 textbook. Before you begin, there are a few topics that I recommend that you review: frequency tables, contingency tables, and risk. These three topics will come up again this week. The numbers that you see here are the sections in the online notes where these topics were first introduced. There are two key topics you're going to focus on this week: the chi-square goodness of fit test and the chi-square test of independence. You'll see that they share some of the same formulas and follow the same basic procedures. The difference is that the goodness of fit test is used with one categorical variable, while the test of independence is used with two or more categorical variables. Let's start by looking at the chi-square goodness of fit test. This test is used with one categorical variable with more than two categories. You can think of this as an extension on the single sample proportion z-test that you learned earlier. A goodness of fit test with two categories is equivalent to a single sample proportion z-test. If you have only two categories, then the single sample proportion z-test is typically preferred. If you have more than two categories, then you would need to use the goodness of fit test. In this test, the observed frequencies are compared to the frequencies that we would expect if the null hypothesis were true. This will also be the case for the chi-square test of independence. The first step in computing a chi-squared value is to determine what the expected values are. The expected count for a cell is equal to n times p sub I, where n is the total sample size, and p sub I is the hypothesized value for the proportion in that group. This is the proportion in the null hypothesis. Expected counts, along with observed counts, are then used to compute the chi-squared test statistic. You will see some examples of this in the online notes and textbook this week. Minitab Express will compute all of these values for you, but you should understand where they come from and how to interpret them. We will be using the 5-step hypothesis testing procedure this week to conduct these tests. With the 5-step hypothesis testing procedure, step 1 is to check assumptions and write hypotheses. In order to approximate the sampling distribution using a chi-square distribution, all of the expected values must be at least 5. If any of your expected values are less than 5, then you cannot use the chi-square distribution. You could, however, conduct a randomization test. StatKey will conduct this test for you. There is an example in your textbook, and you may have to walk through one of these procedures on your lab assignment or in your homework this week. The hypotheses are going to be dependent on what your research question is. Many times we want to know if all of the proportions are equal. Here we have an example like that with 4 categories. If the 4 categories were all equally likely, then all of their proportions would be 0.25. The null hypothesis does not need to take this form, though. It is possible to hypothesize different proportions for each category, but all of these proportions must add up to 1. Step 2, compute the test statistic. We've already seen this formula. It compares our observed and expected counts to compute a test statistic. Step 3, determine the p-value. The goodness of fit test uses a chi-square distribution with k minus 1 degrees of freedom, where k is the number of categories. Step 4, make a decision. As always, if p is greater than alpha, we fail to reject the null hypothesis. If p is less than or equal to alpha, we reject the null hypothesis. Unless otherwise stated, assume that alpha equals 0.05. In step 5, state a real-world conclusion. This is where you would go back to your original research question to state whether or not you have evidence of a difference in the population. Steps 2 and 3 here can be conducted with Minitab Express. You should not be worrying too much about the math in this lesson. You should focus on the underlying concepts. While you won't need to compute the whole test statistic by hand, you will need to know how everything was computed and how to interpret it all. For example, you will need to know how to interpret an expected value. and you will need to know how to compute an expected value. Let's move on to the chi-square test of independence. This tests for a relationship between two categorical variables. In this course, we'll only be looking at examples with two categorical variables. However, it is possible, with slightly more sophisticated statistical software, to do a chi-square test with more than two variables. But as you can imagine, the calculations and interpretations would get much more complicated. So in this course, we're only going to be doing two-way chi-square tests of independence. Each variable may have two or more categories. So the smallest chi-square test of independence that we'll see is a 2x2 chi-square test of independence. 2 by 2 means that the first variable has two levels and the second variable also has two levels. Again, the observed frequencies are compared to the frequencies that we would expect if the null hypothesis were true. The test statistic here is identical to the one that we saw for the goodness of fit test. The expected count formula is different because now we're working with two variables. The null hypothesis, we'll see, is also going to be a little different here. Remember that we're looking for a relationship between the two variables. So the null hypothesis is going to be that there's no relationship in the population, that the variables are independent. If the variables are independent, then this formula gives us the number of cases that we would expect to see in each cell. Again, we will use the 5-step hypothesis testing procedure. Step 1 is to check assumptions and write hypotheses. Again, all expected counts must be at least 5. If this assumption is not met, you could use a randomization test, which StatKey will run for you. Here's the general form of the hypotheses. The null is that there is not a relationship between the two variables, and the alternative is that there is a relationship between the two variables. When you're writing out your hypotheses, you should replace the two variables part with the actual names of the variables that you're testing. Don't just copy and paste these general hypotheses for all of your tests. Step 2, compute the test statistic. This is the same formula as the goodness of fit test. Step 3, determine the p-value. Now, the degrees of freedom are determined by the number of rows minus 1 times the number of columns minus 1. Step 4, make a decision. As always, if p is greater than alpha, we fail to reject the null hypothesis. If p is less than or equal to alpha, we reject the null hypothesis. And finally, step 5, state a real-world conclusion. This is where you would go back to your original question and state whether or not you have evidence of a relationship in the population. Minitab Express will compute the test statistic and p-value for you. It also gives you options to request the expected values and chi-square contributions of each cell. You should be able to interpret all of those values correctly. This concludes the Lesson 9 overview video. If you have any questions this week, please post them to the Lesson 9 discussion board on campus.